Okay, welcome back to the second lecture this morning. It'll be given by Theo Assiotis, and he'll talk to us about stochastic dynamics for the Hua-Pickrell measures.
Okay. Yeah. Thanks for the invitation. It's great to be here. So I'll be talking about the construction of a stochastic process, which is going to have as its unique invariant measure certain measures that are called Hua-Pickrell measures that I'm going to introduce in a bit, that live on an infinite dimensional space omega. So this process is going to have some nice properties. So it's going to be a Feller-Markov process. It has some regularity properties, and it's going to be deterministic. So this allows many probabilistic quantities of interest to be computed explicitly. And then the problem is related to different areas in maths, like ergodic theory, random matrix theory, determinantal point process, stochastic differential equations, and a key part in the proof of the main result is Markov dualities. And so also can be viewed as a non-colliding dynamics on a particle system with infinitely many particles. Actually, it's going to be so you can think of it as these Hua-Pickrell measures give rise to a point process in R star with infinitely many particles. Okay, and then these dynamics are gonna, so time moves this way, are gonna give rise to paths that never collide. And then this is the kind of object I'll be looking at. Okay, let me introduce this space omega. So space omega depends on two sets of infinitely many parameters, and then parameters gamma 1 and gamma 2, which are a bit more mysterious, but I will explain what they are in a bit. So what you should think about these parameters are as the positions of these particles. So alpha 1 plus is the position of the largest position of the first positive particle. Alpha 2 plus is this one, alpha 3 plus is this one, and so on. And then this is one is minus alpha 1 minus, this is minus alpha 2 minus, and so on and so forth. And then this space omega, it kind of looks, arbitrary, but it actually parameterizes ergodic unitarily invariant measures on the space of infinite Hermitian matrices, which is something I will explain in the next slide. And also equivalently forms the boundary of the graph of spectra. This is the name given by Kerov, and now we'll also explain how this correspondence works. Okay. So yeah. So what are these ergodic unitary invariant measures? Okay. So first of all, I consider Hn is the space of n-dimensional Hermitian matrices, and then I consider projective limit, which is just all infinite Hermitian matrices, and then I consider the infinite dimensional unitary group, which is, you can think of it as matrices that are going to be, this corner is going to be unit, so it's going to belong to un for some n, and then it's going to be the identity further on. And then this group is going to act on an infinite Hermitian matrix by conjugation. And then I want to characterize what all the ergodic measures are for this action. And this is a problem considered by Pickrell. And first of all, the remarkable fact is that there is an explicit characterization of these ergodic measures. And then this is given in this explicit form in terms of the Fourier transform of the measure. And this problem this theorem was first proven by Pickrell in 1991 by making the connection with totally positive functions, which were already characterized by Schoenberg in the 50s. So totally positive functions are functions phi, which on the real line, which satisfy the following: the determinant of phi Si minus Tj equals 1 up to n, where the S's are ordered and the T's as well. Then this is positive, and this holds for all n.
I'm not sure people can read this.
Okay, so sure. Write it bigger, sure. Okay. Well, my handwriting is very bad, but yeah, if something is not clear. So the determinant of phi Si minus Tj is greater than or equal to 0 for all n, and s, these s's are order, and the t's as well. Okay, is it clear? So there's a correspondence between ergodic measures on H and these totally positive functions, and this is actually given by, if you just look at the so if you look at the first, the first entry, the 1, 1 entry, then the distribution of this entry is given by these totally positive functions. So Pickrell made this correspondence and then used this theorem of Schoenberg and characterized the ergodic measures. And then in 96, Olshansky and Vershik, using the ergodic method that Konstantin described in his talk, then they gave a different proof that gives more info, actually tells you how these parameters, these infinitely many parameters, the gamma 1 and gamma 2, arise in this setting. So, okay. So yeah, actually these measures are given by convolutions of these more elementary measures where all the parameters, as if you, okay, so if all the gamma 2 and the alphas are 0, then gamma 1 corresponds to just a scalar matrix. And then if gamma 1 is 0 and all the alphas is 0, then gamma 2 corresponds to an infinite Gaussian unitary ensemble, which you just take Hermitian, just take independent complex Gaussian entries, and then subject to the Hermitian constraint, and then this is the measure with this Fourier transform. Okay, so is this theorem? Okay. Is it clear? Okay. So let me move on. Then okay, so how is this connection to this what's called the graph of spectra? So I'm going to consider bunch of spaces En, which are gonna be locally compact, complete separometric spaces. So you can think of them as E1, E2, E3, En plus 1. So this is En plus 1. And then each one of these is going to have a Markov kernel that takes you down. So you can think of this as a Markov chain that moves down the spaces. Okay. And then I will call the extreme coherent, extreme points of all these sequences of coherent measures, which are measures that are coherent with respect to these Markov kernels with these links. I'm going to call this a bounded chain and denote this by E infinity. And according to some abstract theorem, this is a standard Borel space that comes along with a family of Markov kernels that use this kind of map. So essentially, if you like, this is a Markov chain, and E infinity is the entrance boundary for this Markov chain, and lambda and the lambda n. This are the entrance laws for this Markov chain. Okay. So what is the correspondence between? So yeah, I mean, you can. These sort of things arise when these are discrete. Then such construction arises from branching graphs, and yes, I mean, if you have certain these are different levels of the graph, and you have certain multiplicities, then from that you can construct these lambda n's, and then these branching graphs fall into this kind of framework. So okay, so what is the graph I'm interested in specifically? So it's the following. So the ENs are gonna be these Orzer Weil chambers. Okay, so they're gonna be these Weil chambers, and the links are gonna be this ones. So okay, so these are given as a ratio of Vandermonde to Vandermonde determinants, and then this is non-zero if and only if these two sequences interlace, which maybe just draw it here so it's a bit clearer. So this means the following: y1 x. Yeah, that's good. Thanks. And then I have xn, and here I have yn xn plus 1. So I have if the y's satisfy these constraint with respect to the x's, then this gives you a kind of the conditional probability of starting from this configuration to go down to the configuration of y's that's like this. And actually, how do these arise from these random Hermitian matrices? If you just take an n, let's see, n plus 1 times n plus 1 Hermitian matrix, which is unitarily invariant, and then you just cut this corner right here. So it's n, and this is n. Okay, and then if you fix the eigenvalues of this one, so if the eigenvalues of the large matrix are equal to x1 up to xn plus 1, then okay, so this is still a random matrix. The eigenvalues are not random though. But if you cut this corner, then you get now an n times n random Hermitian matrix. But now the eigenvalues are again random. Then, well, I mean, it's a deterministic statement that the eigenvalues of these matrices are going to interlace, so they're going to satisfy these constraints. But in fact, this conditional distribution of the eigenvalues of this submatrix, given that the eigenvalues of this one are the x1 up to xn plus 1, are given by this distribution. Okay, and then this is a computation that appears in the paper by Rezhnikov in the random matrix literature, but actually it goes back to book of Gelfand and Naimark in the 50s where they did this computation. Okay, so if you have an infinite unitarily invariant Hermitian matrix, then it's minor, so the measures on the eigenvalues are going to be coherent because the conditional distributions are going to be given according to this Markov links, and then the correspondence goes the other way as well. So there's a correspondence between ergodic unitarily invariant measures on infinite Hermitian matrices and these extreme coherent measures on these levels for with respect to these links. Yes, sure.
Extension, no? This is standard.
Yes. You mean this thing? Yeah. Yes. I mean, it's a computer. It's not. Yes. I mean, it's a rank 1 perturbation. Yes. Okay. So yeah. Okay. So then, and in fact, okay. So you know that omega is the boundary of this. So have the ends. We have these links. So what is E infinity is omega. But actually, this thing in general is, I mean, it's not explicit, but in this case, it's actually explicit. When there's a Gaussian component, then, okay, so there's a notion of extended totally positive functions, which these are the j minus 1th derivative. So these extended totally positive functions satisfy that these determinants are positive. And then the Markov kernel from omega to the WNs is explicit and it's given as this, it has this form. And then this is given, its Fourier transform is given by f omega. Okay, so that's the course where you have, I give you a point on omega, then I get this extended totally positive function, which is, I mean, its Fourier transform is explicit, but in general, this function is not, okay, it doesn't necessarily have a very nice form. Then you form this Markov kernel, and then you get lambda infinity. Okay, so is this kind of clear, the construction? I have something that looks like, I mean, it's not actually a graph because the ends are not discrete, and I have a Markov chain that goes down, and I know what its boundary is. Okay, so this is the way Olshansky and Vershik prove this theorem. So how is a measure mu on omega? It corresponds, as I said, through these Markov kernels to a coherent sequence of measures on these WNs. But how is it actually concretely relates it? So if you have the following embedding of Wn into omega as follows. Okay, so these are just so essentially I just split them and divide by n. So the ones that are positive I'm going to call them alpha 1 plus. I'm going to call this one alpha 1 plus. I'm going to divide this by n and call this alpha 1 plus n. I'm going to divide the next one by n and then call this alpha 2 plus. And then this one I'm going to take minus this one over n and call this alpha 1 minus and so on and so forth. And then I'm going to take the trace and then this sum of squares, and the theorem is as follows. Then I get a measure, so I'm going to get a measure of omega, and then this measure converges weakly to these to the measure mu. So essentially, if I pick the xn's according to mu n, I do these embedding into omega, then these random variables are going to converge to these random variables which are picked according to a measure mu on omega. Okay, so this is an approximation procedure because my construction is going to be a bit abstract, and then using these can tell you how you can actually approximate this stochastic process as well. Okay, so I'm going to come to the Hua-Pickrell measures now. Okay, so these are measured on Hermitian matrices. I'm going to define them for a real S greater than minus 1/2, so that these can be normalized to be probability measures. And then these are given by this following form. So this is Lebesgue. So this is the Lebesgue measure on Hermitian matrices. Okay. Well, actually, you can define them for real S less than or equal to minus 1/2, and then but then there's a lot of new ideas that are needed to actually study them. And the key fact about these measures is that they satisfy some consistency property, which means as follows. So if you take this density, and then you integrate out this part, then the measure you get here on the n times n, one is going to be, again, it's going to have again this density with a difference constant, and then these use this sort of matrix integral of Hua log Yang. Okay, and there's another fact. So these measures, okay, so these are consistent, so they give rise to a measure on infinite Hermitian matrices, so a measure omega, and you want to study the ergodic decomposition, and this has been studied by Borodin, Olshansky, Sasha, and Yanshi. So this is I mean, okay, so some parts are very delicate. For example, studying the behavior of these kind of parameters is okay. So if we look at the radial part, we get these measures on Wn, which is given as a square van der Waals determinants times this product of weights, and then these are consistent with these links. Okay, so this follows by this one. And then you get a measure on omega, which are, so these are the measure that I'd like to construct a stochastic process that lives in invariant. Okay, so you can also, under the K transform, you can go to a measure in the unitary group, and for example, for s equals 0, this goes to our measure. So, okay, so in general, I mean, maybe, so it would be, okay, maybe I'll comment about it at the very end. So you can construct a process as well that leaves a matrix process that leaves these invariant. It satisfies certain nice properties, but so from now on I'll only be interested in these. So these measures have some extra nice properties. So actually they form a determinantal point process. So I mean, we've already seen the definition of determinantal point process, but I'm going to give you another one here. So these k-point correlation functions are defined like this. So this is if I have a fixed number n, number of particles n. So the probability that exists a particle in this infinitesimal interval xi from I equals 1 up to k is given. So this is the definition of the correlation function, and this is in fact given as a determinant of this function of two variables, the correlation kernel. And this has actually even more structure. This is given by an orthogonal polynomial ensemble. So this kernel is given by the sums of these polynomials which are orthogonal with respect to this weight, and this weight is this thing here. Just if you just forget about the j's, just take n equals 1. So and then using Christoffel-Darboux formula, you can write this as just a difference of product of two polynomials, and then studying. So the problem of studying asymptotics, sending n to infinity, boils down to studying asymptotics for orthogonal, one-dimensional orthogonal polynomials. In this case, okay. So now we're going to consider this. So I'm going to use this general method of Borodin-Olshansky, which they introduced to construct dynamics. This is a thing of branching graphs, So you have measures on each level, and then you want to, and then you have a boundary corresponding to that graph. You have a measure on the boundary, and then you want to construct a natural stochastic process that leaves that measure invariant. And then what you do is you construct stochastic processes that have these finite n measures invariant, and then they satisfy a certain nice relation, consistent relation, which I'm going to explain. So, well, first of all, I need that these semigroup is Feller Markov, which means they preserve functions vanishing at infinity, and it's strongly continuous in T. And then I also assume that these are Feller. Okay, so there's no time here, so it's just that they preserve functions that vanish at infinity. And then, moreover, I assume this intertwining relation, which I'm going to try to explain what it means in terms of the. So we have a Markov chain going down, as I said, and then we have and now we have another Markov process which moves this way. So lambda m plus 1m. Okay, so this relation means, okay, so you can start by running these, you can run this Markov chain and then run this one on this level, on En. And it's the same, so you're gonna end up with some distribution here. So this is the same as first running this Markov process on this level and then running the other Markov chain down. So, okay, if you have this relation, then there exists a unique Feller semigroup on the boundary such that it satisfies this sort of relation with the projections on the finite levels. And then you also have this extra, so if mu n is the unique invariant measure for each of the Pn, then mu infinity, which is the measure corresponding to these, then is the unique invariant measure for P infinity. So if this is unique invariant measure for Pn, then you get that these measures are automatically coherent for free. So there exists a measure of mu infinity on infinity. Okay. So this is okay. So I gave you the method. So I gave you the measures and also gave you the method of how I want to construct this process on infinity. So now the question is, do there exist Markov semigroups that satisfy these coherency relation and also preserve these Hua-Pickrell measures? And the answer, well, the answer is yes, and it's given as follows. Okay, so this Markov process is given as the solution to these stochastic differential equations. So yeah, I mean, you don't really need to think too hard about this, but okay, so these are Brownian motions, so this is the random term. And then there's a repulsion as well. So if particles get very close, then they repel each other. And in fact, this gives rise to non-intersecting paths. So the particles never collide. And also they satisfy some even stronger property. So you can even start all particles from the same point and they're going to instantly separate. Okay, and then, well, I mean, you can prove that this is Feller, and then this is a unique invariant measure for these SDs. Okay, and how do you do that? Actually, so there's a more structure to the problem because actually this Markov process is exactly solvable in a certain sense that I will describe now. Okay, so the Markov kernel, the transition probability, the probability that tells you if I start from locations x1, x2, x3 at time 0, and then I want to go to at time t to locations y1, well, being a small interval around y1, y2, y3, then this is given explicitly by this group, by this kernel. So this is given. So this is a dupe transformed by the Vandermonde determinant of this sub-Markov semigroup, which corresponds to the following. So you just take n independent copies. So you take n independent copies of these one-dimensional diffusions, and then you're going to. So they're going to intersect, and when they intersect, you're going to kill them. And then this is conditioning these n independent copies never to intersect. This is Dupes conditioning. And so again, the problem, so this is a n-dimensional problem, but it again, kind of dynamics can be described by these one-dimensional copies that are conditioned not to intersect. So you get this determinant, this one-dimensional kernel, and then this has this generator, and this is reversible with respect to this measure. And obviously this measure is exactly this, the measure that comes in the Hua-Pickrell measures. Okay. So, well, and are they consistent? Well, the answer is yes. So you can prove that these are consistent with respect to these links. And then by the theory I described before, you get this unique Feller semigroup on omega, which has this measure as its unique invariant measure for real s greater than -1/2. And then a key point, the proof is played by something that's called the dual Hua-Pickrell diffusion, which is again a one-dimensional diffusion process. It's a strong Markov process with continuous sample paths. That's a generator of a very similar form. So it's the same diffusion coefficient, and then the drift is a bit different. Actually, it's 2 minus the drift of the other one. And then they satisfy a very amazing relation, which is as follows. So if I start the process with zt from x, and then I want to end up below y at time t, has the same probability as starting the hard process from y, and then I want to end up above x at time, let's see, at time t. So these give you a relation between the transition kernels. Then they give you a relation between these transition kernels and the ones corresponding for the dual diffusion. And then another key thing is that you can actually transform this one-dimensional process that has an n, transform it to be equal to, by conjugation, to be equal to this one with n plus 1. So again, this boils down to computation between one-dimensional transition lenses, and this is the key. Okay, to do this. Okay, so this is an abstract construction of this process on the boundary. So how is this actually related to this process? And the answer is it's actually through this approximation theorem. So we can still embed the paths into omega by just dividing by n and just splitting the positive and negative parts. And then we can prove that these, if you start from coherent measures, then you get, at time t, you also get coherent measures. So the statement is, you start with finite n, you embed this process into omega. Then, if you started from the sequence of coherent measures, then at fixed time t, this converges to x infinity t. If this is started, so if these are coherent, and this is a measure corresponding to the sequence on omega, then you're gonna get these converges to this x infinity process started from the measure mu. Okay, and then this, I should say, completely describes x infinity because it gives you a distribution from starting from. In particular, you can start from any fixed any point on omega, any deterministic point on omega. So you just take coherent sequence of measures that converges to this point on omega, and then you get this distribution. Okay, so let's see. So is it clear how the construction works approximately? Any questions? Okay, so let's see maybe just a couple more things about what this construction, how this, you can get, so from this intertwining relation you can construct something else. So you can construct a process living in this Gelfand-Zetlin pattern. So where you have an array where all the levels interlace. And then, if you started from a measure of this form, so you start the process, so the particles are going to be, all these particles are going to be independent one-dimensional diffusions, and they're going to interact with each other in order for these constraints to hold. They're going to interact by, so this particle is going to reflect of the paths of the particle at the level below, and so on, so that the interlacing remains. And the theory, if you started from measures of this form, which is, have a certain measure on the top level, and then you have the conditional distribution are given by these Markov kernels. So essentially, what you get is the conditional distribution of the rest is uniform. So at time t, and you run the dynamics that I kind of described. So at time t, what you're going to get is, so you're going to evolve this measure according to the Hua-Pickrell diffusion, and then the conditional distribution is going to remain the same. And then similar construction appear in many integrable probability models and so on. And then in this model you get here, so you get particle systems with one-sided collisions, which are the continuous analog of the totally symmetric exclusion process, but now a diffusion that drift dependent position. And then also something else that I did is I described processes on eigenvalues, but then you can construct a process on matrices that leaves the matrix Hua-Pickrell measures invariant, and then using that process, there's a classical identity of Bouguereau for Brownian motions, for one-dimensional Brownian motions, and then I extended this to the matrix setting, and then you can construct the measures that these measures that I showed you here. You can construct these as stochastic integrals involving matrix Brownian motions. Okay, so there's a question, of course, where this matrix process actually satisfies the consistency property. So if you have a process and then you just cut the corner, is the process consistent in the sense that as a Hua-Pickrell measure, if you cut the corner, then you get again a Hua-Pickrell measure. So if you do the same at the process level, do you still get a process of the same form? And then the answer is I don't know. Don't know that. I hope so, but it's not clear. It's not clear. Okay, and then we should just briefly mention some work in progress. So we just using the form of this semigroup, we can calculate. There's a notion of the semi-answer point process that involves time, that has a kernel that also involves time, and then using this special form that is given by these determinant transition functions to go from one time to the next, you get a determinant involving a single function and then the points here and here. We can prove that these processes are actually extended semi-answer point processes, and then we can compute kernels starting from the stationary and from arbitrary deterministic initial condition. And then the next task is to take the limit as n goes to infinity of these correlation kernels, and also prove that these sample paths are continuous of the infinite process, and construct equations for the process, because right now they have no equations for the infinite process as well. Okay, so yeah, so you should say in the random matrix. So this method of constructing processes in constructing these processes using, so it wasn't used in random matrix theory before. So the previous methods for constructing processes with infinitely many particles that live in very uncertain processes coming from random matrix theory was through these extended correlation kernels or stochastic differential equations. And then those methods they cannot start it from any arbitrary initial condition. So this is new as well. Okay, so yeah, I guess that's it. Thanks.
Questions?
Yes.
I need to give you the microphone. I've been told.
So, do you have some recipe or something? So maybe it's a stupid question, I don't know. To find the stochastic differential equations that for which your Hua-Pickrell measure will be invariant measure. So how did you find them?
Oh, you mean how did I find out the theorem is true? Yeah, well, I can explain this in more detail. Yes, okay, so first of all, you start from n equals 1 case. There are many, you have a lot of choices of which one-dimensional diffusions are going to have that one-dimensional measure invariant, and then you need some extra properties. So you'd like this Vandermonde determinant to be an eigenfunction for copies of them, and then essentially you get this. If you know what you're looking for, then it's yes. But yeah, I can explain in more detail. Private, yeah.
Thank you.
Any other question? Huh? Sasha. See, it feels like we are on some international congress.
Right. So, but just this, it comes to Pierre's question. What about diffusions that preserve Pfaffian processes? So what?
Yeah, it's a good question. It's not clear that I'm not sure whether. Well, this approach is not going to work. Are there any examples that I think yes? Osada has some examples, but it's a construction of SDs that leave these invariants, not necessarily. You don't. In some sense, this process has all the it's determinantal, and it's given by these transform of one-dimensional things. So maybe you can construct a process that is going to leave those measures invariant, but then are you going to get all these nice processes? I don't know. I don't think so. There are no examples.
Any more questions? We have time. No? If that's not the case, let's thank Theo again. And we will reconvene at 11:30. Okay, welcome back everyone. The final talk in this morning's session, will be given by Milton Minervino on tree substitutions and Rauzy fractals. Thank you.
Thank you very much. First of all, thanks to the organizers for this beautiful conference and invitation. So, today I will show you something about symbolic dynamics. So there are two main subjects in my talk. So the first one is tree substitutions and the second one is Rauzy fractals, but they are quite related one with the other. So the aim of the talk is to show you how to construct these trees that are inside some fractal shapes that are called Rauzy fractals. So these things I will try to explain to you today. And so to each substitution that is a combinatorial object of this kind, you can associate a Rauzy fractal and you can associate a tree substitution which generate this tree. This is just only some panorama of what we get in some sense. So these are trees for different substitutions. And so we will see if at the end of the talk I will have been able to tell you how to construct these things. So we start with my main example, and my main example along all the talk will be the Fibonacci substitution, it's called. So it's the substitution sigma, which is defined on 3 letters, A, B, and C. So it's very easy rule, symbolic rule, right? So every time that I see an A, I substitute and I put an AB, concatenate together. Every time that I see a B, I put an AC. Every time that I see a C, I will put an A. So you start with a letter A, and you apply the rule AB. I do it 2 times, and so I will get A, B, A, C for concatenation, and so on. All right? So it's easy. It's just endomorphism of the monoid of words. Click, click, click. And if I do it infinitely many times, I will get an infinite word, right? On 3 letters, A, B, and C. Great. So this substitution is a very particular one. I didn't choose it like that randomly. It's a very, very famous one and very particular one. Why? First of all, well, it generates words which have very low complexity. So this you can prove it, it's quite easy. In this case, in particular, if I take the complexity of this word, so the number of subwords of length n, this is 2n plus 1. Second, well, to every substitution I can associate an incidence matrix. So I put in the columns the occurrences of what is in the images, no? So I mean the first is sigma of A, I see an A and I see a B. So 1, 1, 0, no C. B, A, C, so I see an A, no B, 1 C. Okay? C, A, 1, 0, 0. That's it. This matrix is a characteristic polynomial. And, okay, yes, this matrix also is primitive. I mean, there's a power such that this matrix becomes positive. And the most important hypothesis, the dominant root of this polynomial is a Piso root. So what is a Piso number? Just to recall, it's an algebraic integer, lambda greater than 1, such that all its Galois conjugate except itself, of course, are in modulus less than 1. So this will be a key property for the entire talk, Piso substitutions. And so what else? Okay, yes, I will denote by U the dominant eigenvector. In this case, that will be also the frequency vector. And so with this hypothesis, I call sigma, the Fibonacci substitution, a near-reducible unit Piso substitution. So Piso is because lambda is a Piso number. Irreducible is because this polynomial is irreducible over Q. And unit is because also lambda is an algebraic unit. Okay? Or the matrix is invertible. Let's see. So this will be the setting. When I have such a substitution, I consider a dynamical system. The dynamical system is a subshift. Subshift, I mean, it means that I take all the bi-infinite words over the alphabet of the substitution, which have whose factors, those little blocks that I see in these bi-infinite words, are inside the language of the substitution, so that I can see as a factor of some power of the substitution on some letter. Okay? So there's a language. I build all the bi-infinite words in this language, and I put it in X sigma. Okay? So this is a set, and the dynamics is basically given by the shift. I shift the sequences. Okay? For a primitive substitution, so for when I have a primitive matrix, I have all these nice ergodic properties. So this subshift is minimal, is uniquely ergodic, and with 0 entropy. So it's something that we still want. There's still some things that we don't know. We would like, for example, to know something about the spectrum of this subshift. Okay. So this is the main setting. Right now we will use furthermore the Piso hypothesis to build a geometric representation for these subshifts. Okay. So again, I take this Fibonacci substitution. What I can do is I can take this word, so the fixed word that I showed you before, and I can abelianize it. Abelianize it means that I use this L function here. So to every word P, I just count the occurrences of the letter I, and I put the vector. So what it means basically that every A becomes a vector E1 of the base in R3. Every B becomes a vector E2. Every C a vector E3 in R3, right? So if I abelianize this word, basically I construct this stepped line which goes to infinity like there. Okay? Is it okay? So I start from 0 and I see A, so I go to E1, then I see a B, so then I go to the direction E2 and so on. The piezo property allows you to say that this line doesn't go randomly somewhere in the space, but goes to a very fixed direction. Okay? There's one direction where this line will stay at bounded distance. Okay? And this is the piezo property that gives you this very important information. So this is what we call balance in the symbolic setting. So piezo property implies balanceness. And so the stepped line stays at bounded distance from RU. Okay? Did you see? It's too slow, yeah. Well, too low. So this property also gives you the way, and so this was Rauzy's idea of the 80s, to give a geometrical representation to these subshifts. So what is the Rauzy fractal? I have my space R3, right, where I'm doing these things. I have a decomposition of this space in a unstable space and stable space. This is given by the matrix of the substitution, right? It's an hyperbolic matrix, so I have an unstable space of dimension 1, in this case, and a stable space of dimension 2, a plane. This word here, I have interpreted as a line, as this stepped line, okay, by abelianization. So what I do, this line goes along this unstable direction. So I take this stable plane here, and I project the vertices along the unstable direction to that plane. Very easy. Okay? So this is what I wrote here. I take the abelianization of the word that I see here, I project it down, and I color the point according to the successor of what I'm projecting. So if example is here, the first thing that I project is the empty prefix, 0, the 0 point, right? And I color it by red because the successor is A. I project it and it's here. The next one is A. A is abelianized by E1, and I color it by blue because the next one is B, and is here, the projection, and so on. AB is again red because the successor is A, and it will be there. ABA is green, okay. So I do this, take the closure of this projection of points, and I get a beautiful Rauzy fractal. So these three compact domains that are living in this contracting space, right? Okay, so I think that most of you already saw these pictures. Moreover, this one for the Fibonacci substitution. So this thing, I mean, it's compact because of the piezo hypothesis, and I can construct it because of the piezo hypothesis, basically. This thing comes equipped with this. So again, I do it all the time, and I like it a lot. So it's a very amazing thing that happens here. I mean, you can translate this red thing there, the blue down there, and the red one, the green one up. And this gives you a domain exchange and still makes the Rauzy fractal, right? So this domain exchange is defined as exactly like each subtile labeled by I is translated by the projection of the basis vector EI, okay? So this is something that does not happen only for the Fibonacci substitution, but for every unimodular irreducible piezo substitution. And this was proven in 2001 by Pierre Arnould and Shunji Ito. So this, what is the domain exchange? Basically is the shift when in the symbolic setting. So when you are shifting in your subshift, you are doing this domain exchange in the Rauzy fractal, okay? And this is so a measure conjugation. Okay. Yeah, sorry. Yeah, of course. I always forget this. I mean, this is something very, very important to say. The strong coincidence condition is a combinatorial condition of the substitution, which is true, for example, for Fibonacci substitution, which says take no matter which two letters of the substitution that you have. And there exists a power of the substitution such that these two letters evolve under the substitution. They make two prefixes that in abelianization are equivalent. And then there's a coincidence. There's the same letter. Maybe I should write it somewhere. So this basically is a condition to say that the cylinders, so I mean these three things here, are disjoint in measure. This is fundamental for this reason here. So maybe I write it here, the strong coincidence condition. SCC. So for any A1, A2 in the alphabet of the substitution, there exists a K in N, and there exists a letter C for coincidence, such that sigma N of A1 is equal to some prefix P1 C suffix S1, sigma N of A2 is equal to some other prefix P2 C S2, and P1 and P2 have the same abelianization. Okay, but that's the coincidence there. So this is a condition that is supposed to be true for no matter which Piso substitution. So it's kind of equivalent of Piso conjecture also, maybe, I don't know. But I mean, I will tell you what is Piso conjecture right now. So this is the first thing to know. I hope that it's not my thing here. The second thing is this question. I mean, when you have the entire Rauzy fractal, you can ask if this tiles the space where it lives. So in this case, it's true again. I mean, I show you a picture of this periodic tiling made by the Rauzy fractal, the full. So I mean, the one that I showed you before was with the 3 subpieces. This is the full one. So the question is, do we have periodic tilings by these fractals fractal domains? And this is very, very crucial question. So this is why Rauzy invented all the thing in some sense. Because if it's true, if it were true, then the Rauzy fractal becomes a fundamental domain for a torus, right? In this case, it's a fundamental domain for the two-dimensional torus. And the domain exchange, it projects on this torus to a translation. This is exactly what I wrote here. So this means what? This means that my system, my symbolic system here, which was already measurably conjugate to this domain exchange in the Rauzy fractal, becomes a toral translation. I mean, it's measurably conjugate to a toral translation. This means that is pure discrete spectrum. Okay? And this is what basically Piso conjecture says. And so it's a 35 years old problem, which is still unsolved. And it's quite easy to state. I mean, take a Piso irreducible unimodular substitution, then the symbolic shift generated by this substitution is pure discrete spectrum. And so Rauzy did this thing, this Rauzy interpretation to show that you can get something like measurably isomorphic to a translation on a torus, which is equivalent to this thing. So this means that every word that we see basically in this subshift, they are codings of this toral translation, according to the partition given by the Rauzy subtiles. Okay. So this question here, of course, if this Rauzy fractal tile the space, is very important. I mean, still nowadays it's unsolved. And so what do we know exactly about this conjecture now, today? So many things, but so for example, of course, it's true for substitution on 2 letters. This was shown long ago. For Piso substitutions on 2 letters. It's true for some special classes of substitutions. For example, the last result by Marcy Barge was that it's true for example, substitution injective on initial letters. So you see all the letters on the first place, and constant on final letters. You see always the same letter at the final place. Some special class of substitutions. There are many algorithms, geometric sufficient and necessary conditions to check if the conjecture is true. There are many people who have worked on these things. So I just cite some of them here. Akiyama Lee, Fruni Solomiak, Sieven Solomiak, Itorao, and so on. Many things. And they just tell you that this is false if you just go out, if you go beyond the irreducibility, or it's not anymore true. Okay. Questions so far? So I show you images in the meanwhile. It's amazing because, I mean, there are many people who have been working on Rauzy fractals and who have been working also on programming. So right now it's very easy to put on Sage, for example, I don't know if you know Sage, if you use Sage, a word morphism, so a substitution. You plug this substitution inside Sage, and there's a property of the substitution that says Rauzy fractal plot, and you get beautiful pictures like this. If you want to impress somebody with some strange topology, I mean, as you see, I mean, what I showed to you, the Fibonacci Rauzy fractal is quite special because it's a nice one, let's say, but there are very nasty ones, like not simply connected things, whatever. So, I mean, topology of fractals, of Rauzy fractals can be quite strange and hard to deal with. Okay, so right now I go a little bit more in the direction of what I want to say. So we want to get a tree out of it. The first ingredient, it's induction, of course. So what is induction in the symbolic setting is to desubstitute words. A very old result says that if for every word in the subshift that we are considering can be desubstituted uniquely almost. In what I mean, it means that I take this W and I can find a W prime such that its image, eventually shifted by a little bit of set, will be again W. And this is parametrized by, this is parametrized by a path in a graph of the substitution. Maybe I show you first an example. So I have a bi-infinite word here, okay, that is in my Fibonacci subshift. What does this mean, desubstitute the word? It means that it's that I can exactly decompose this word in this way. This is a decomposition to see that, okay, here I see an AC, an AB, an A, so this means that this is the image of a B. This is the image of an A, this is an image of the C, and so on. I mean, it's a recognizability of the word. I can put these brackets. I know exactly how to devise this and to put a pre-image, right? So this I can do it, of course, infinitely many times. I mean, now I can find again the brackets for the second word. So here that's what I was calling the offset. I mean, B goes to AC, but with a little offset. Now I'm shifting this letter to the left.
And this can be done in a unique way?
Yes, I mean, this can be done for any word. Yes. But the map that gives you this decomposition is onto, continuous, and one-to-one, except on the set of periodic points. This will be quite important, but I mean, if you don't take periodic points for the substitution, this is unique. Yeah. So I mean, this you can play it like that, you know. And so I mean, what is the address of this first word that I was showing? Is basically a path. So I mean, I'm starting with C, that is the letter, the 0th letter of the word, and I'm putting this sequence here: B that goes to C, A that goes to B. So B that goes to C with a prefix, A that goes to B with a prefix, and so on. Then I didn't show you all the substitutions again. But so you have an inverse path that codes this word. And this path is chosen here in this prefix-suffix automaton is called of the substitution. What it is basically this, I mean, if you know what a Bratelli diagram is the Bratelli diagram of the substitution. The stationary Bratelli diagram of the substitution. Because at each level I have always A, B, and C as vertex, and the arrows are just only where I'm going from the Bratelli diagram. Okay, so this is a very important tool that we use, this substituting words. So this is why we are dealing with only stationary subshifts. So I mean, the induction process here is always the same substitution. We could do something non-stationary, of course. Great, so second step, second ingredient is self-similarity. This is also very important. Self-similarity, this comes from the substitution again. If I take the cylinders of my subshift, these cylinders have this decomposition. Why? Because of this substitution. This is just this substitution here. So each cylinder I can be written as a union of copies of sigma of j, eventually shifted, for every j that goes to I in this prefix-suffix automaton. This is this substitution exactly. And this similarity gets down to the Rauzy fractal, of course. So here I showed you before how to define a Rauzy fractal by projecting vertices from a stepped line. But you can also define it more directly like this. So there's the map phi, which goes from the subshift to the Rauzy fractal. To every bi-infinite word W, you give this point, that is the sum of n sigma to the k, but this is a contraction in the space where the Rauzy fractal live, with these digits, and these are only the prefix that you see in this prefix-suffix automaton. So this series converges to one point. The action of the shift is a translation, is the piecewise isometry that I showed you before, the domain exchange. And the action of the substitution sigma is just the contraction by m sigma. Okay? And so this self-similarity here, with this phi map, gets translated in this nice iterated function system for the Rauzy fractal, which is directed by the graph. That is the prefix-suffix graph of the substitution. So for Fibonacci, again, an example, just to digest things. Again, I have this graph. So what the self-similarity says is that the copy, for example, R of A, I have to see where the arrows are coming inside, the incoming arrows. So R of A is the union of shrunk copies of itself, of R of B, and of R of C. Is what is written here. So I mean, you can imagine that the red one is exactly the union of these three copies, but shrunk inside. And so, yes, it's a very, very important self-similarity. Third ingredient, singular words. So singular words are, I mean, we've heard about many talks on more geometrical talks. For example, just if you think about interval exchange transformations, there are of course some points which, if you try to code them, if you try to code their trajectories, they have more than one coding, of course. There are singularities, right? I mean, if I take the point between two intervals, and the interval goes here and the other there, I will have a splitting of the codings, right? So these are exactly singularities, but symbolically, in a symbolic world. So, Fibonacci substitution again, we look for some things that is called a singular word. So what is a singular word? Is something that, what are singular words? Is something that they share the same future or the same past, but they branch at some point. They have different codings. So for Fibonacci, it's easy to see that if I iterate, for example, 3 times A, B, and C, I get these words here. And the first one ends with A, the second ends with B, and the third ends with C. So it means that I have a way to prolong these words in this direction, right? Always starting with A, B, and C. So I mean, by doing this, I can find these 3 words with ends with A, B, and C. And then I take just a fixed point there. So I attach these things, and I find bi-infinite words which are singular. So which are in the language, which are in the subshift, and which have this structure, which branch in the past, and which have the same future. Okay. There's a funny thing that is called, in the theory of free group automorphism, is called a Nielsen path. So it's this thing here. So I start with these three words, A, B, B, A, and C, A. And again, I iterate 3 times the substitution. What I get is that since, again, A, B, and C, they start with the same letter A, iterating 3 times, I have the same prefix for the 3 words, and then they branch. Okay? So this thing, again, allows me to find other 3 words, this time sharing the same past and having 3 different futures. So thanks to a Nielsen path, I can build, by conjugating with an inner automorphism, 3 words like this, which are in the language again, which are in the subshift of the substitution. And that's all. These are the 6 words that have this kind of weird singularity behavior. So we want to count them, so somehow. Given a subshift, given a substitution, we want to count these singular words. And this will be the notion of index of a substitution, of a subshift. So properties, any primitive substitution has only finitely many such singular words. And if you look at their address given by this substitution path, in particular you find another quite particular result, that they are eventually periodic, the substitution paths. And so for these first 3 words here, the substitution path is the same. Is this one. It's always A. It's abbreviated to be A. And for this 1, 2, and 3 here, WA prime, WB prime, WC prime, they are this one here. And so I call them singular words. Why? Because they have different addresses, but they identify in the Rauzy fractal. So it's exactly the same philosophically, morally, the same thing as a singularity. So if I project them down to the Rauzy fractal, the first 3 goes, the 3 of them to 0, and the last 3 to a point P that is, so they identify them there. Okay? So what I said, so you have to count words that are singular. So you want to count them in a strange way, but not so strange. So a normal word like this, by infinite, I don't want to count it because it's not something singular. But something that branches, for example, like this, is singular. The 2 words, 1 and 2. But this I counted 1. And something like this, I will count it like 2. So I take the ends of the word and I do -2. Okay? So this is how I count singular words. So if you count this like this, you can see, this is a result of the 98 by these 4 guys, that the index is bounded above. So the number of singular words is bounded above by 2 times the size of the alphabet -2. And this is true for any substitution which is also a free group automorphism and which is EWIP, that is kind of fully reducible. So it's I will tell you what it is. And if this is an equality here, so we'll call the substitution parageometric. All right. If this bound is attained, I will call this parageometric. And for example, for Fibonacci is parageometric because this amazing equality holds. 2 times 3 minus 2 is equal to 4. Because I have 2 words like this. I have 2 things that branch like this, and so I have 4 as index. Okay, dictionary, just only for those who don't know. Free group automorphism here basically mean that the substitution is invertible. In this case it is. And an E-whip substitution or E-whip free group automorphism is something that such that its powers fix no proper free factor, which can happen, of course, and I don't want this. So this is an example when something goes wrong. Questions? No, you're hungry? Yes, Carlo, you're hungry? Okay, so there's something, and there's one expert, very expert in this room. So don't ask me things about these things. If you're in this parageometric case, there's something that's called a repelling tree associated to the free group automorphism. How we can see this tree? It's an abstract tree, but basically, if you take the transitive closure of the Shearer-Half relation, the Shearer-Half relation is for words. So again, if two words share the same past, I say that they share a half. If two words share the future, they share also a half, and so on. So if we take this equivalence relation, the transitive closure of this Shearer-Half relation, and I take this quotient, so the subshift mod this relation, I have a tree. This is the result of Gaboriau, Jäger, Levitt, Lustig, and also by my collaborator Thierry Coulbois, Arnaud Illion, and Martin Lustig. So this is true for any E-whip parageometric free group automorphism. Then you have a tree that is called a repelling tree, or the free group automorphism. And this tree comes with a minimal action of the free group by isometries and a contracting homotety H. And when I'm in the subshift X sigma, of course I have a quotient map as well, which goes from X sigma to this repelling tree. What does this quotient map do? Basically, it identifies words that are singular like this. Identifies in the tree these words to the same point. Okay, and it translates so the shift action on the subshift to this action of the free group, and the sigma, the substitution to this homotety. So basically, I mean, what I told you before about the Rauzy fractal happens also for this tree. I mean, we have exactly a parallelism of what it happens. I mean, the Rauzy fractal, again, I use the map phi to say that the shift was translated to the domain exchange, and the substitution was a contraction. The same is true for the tree. The shift under this map Q is a partial isometry, and the sigma is a contracting homotety. It's exactly the same picture. Okay? And so this was the beginning of collaboration with Thierry for me. Thierry Coulbois, my collaborator in Marseille. So we came from these two worlds, and we wanted to see the same thing, so to say. Associated to this subshift, there is this tree, there is this Rauzy fractal. Why not to see this abstract tree inside the Rauzy fractal? So it seems reasonable, right? I'm checking if you are still awake. So the double aim is the first, so to get an abstract tree substitution that gives me this omega sigma. And the second one is, once we have this tree substitution, okay, to embed this tree inside the Rauzy fractal to get maybe some more information also, the dynamics of what's happening, so on. Okay? So double aim. This was the double aim. So briefly, I just tell you, I have still some time, right? Briefly, just tell you what are the axioms of a tree substitution. It's something that you can define abstractly and axiomatically. So I have something that is called proto-tree. It's a little bit weird as a word, but it's like this, proto-tree. So it's a collection of simplicial trees. But each tree comes equipped with a set of gluing points. Okay, I have a tree, then I have some gluing points that I can use to attach something. Okay. Then I start with an initial patch. So I take some trees, I glue them somewhere where I can with some gluing points, and this is, I call it my starting patch of trees. And then I define the toe tau, the substitution on each of my proto-trees, saying, okay, this proto-tree Wi is sent to, I don't know, W1 glued with W2 on this point. I define the substitution on each of the basic trees that I have. And then what still remains to do is to say, okay, tau, the tree substitution, maps the gluing point of each of these Wi to where do they send the points? Where does it send the points? These I have to define also. So these are the axioms to define a tree substitution, right? An abstract tree substitution. Okay, in our framework, it's a little bit rich because we have some self-similarity, we have some more structure. So the gluing points of my trees will be given by exactly this kind of things here. Because I know that they are identified in the Rauzy fractal, that they are identified in the repelling tree. So the gluing point will be my singular words with the map phi applied to them. So singular words are the gluing points, basically. And the tree substitution that I will define reflects, of course, the self-similarity of the object that I'm dealing with. So the subshift or the Rauzy fractal. So when I will define the tree substitution on my Wi tree, I will have here the same instruction rules. So I will have always something ruled by this graph of the substitution, okay? And then I have to say where the gluing points are sent by the tree substitution. And so this also you can easily calculate using self-similarity. I mean, once you have these addresses for the singular words, you know that a singular point is mapped to another one just by forgetting the first state of its address. So this you can calculate basically. So what is you behead at the substitution path to know where the point is sent. It's a little bit technical, but it's just like a computation. Okay, so again, for Fibonacci we have these three words, for example, and I know that these three words, which are exactly something like this, 1, 2, and 3, they identify the same point P in the Rauzy fractal. So how I will start for the Fibonacci substitutions with three trees: the tree associated to the letter A, the tree associated to the letter B, and the tree associated to the letter C. And to each of these trees, I have to define some gluing points that I want to use. Okay, these gluing points are chosen this way. So this is one, of course. P it will be a gluing point, and the gluing point of the tree labeled by A, it will be all the substitution path which ends with a letter A. And these are finite. Why? Because if I look at these 3D substitution paths, since they are eventually periodic, everything that will end with A, at a certain point, I will collect everything. I mean, I will have no any more points to add. So this is one, for example, no? A, and this is the substitution. And another one will be when I end here and not here. And the third one, it will be when I end here. But then I see the same points also in the other. And this is true by ultimate periodicity, so to say, of these addresses. Okay? So basically what I get is 3 gluing points for the first 3, labeled by A, 2 gluing points labeled by B, because I see 2 possible substitution paths ending by B, one here and the other one here, and that's all. And one only for the tree labeled by C, that is this one. I show you the trees, maybe it's better. So I get this tree, this is the first tree TA, this is TB, and this is TC, with the gluing points chosen like this. And then I apply the tree substitution. So I mean, I told you that I need the self-similarity of what I was considering before. So as I had the self-similarity for the Rauzy fractal, I will have the same for the tree substitution. So it means that a copy of the A tree will go to the union of the three of them, glued in the point P. The tree labeled by B will go to a copy of A translated. And the same for C. Goes to a copy of B translated. So I have a way, well, basically I have an algorithm. Maybe you didn't get all the details, but it's normal, I would say. I have an algorithm to find the gluing points, given a substitution, and to put, of course, a simplicial structure to get some trees, and by self-similarity to define a tree substitution like that. I hope I convinced you. So you iterate the substitution, you start to iterate. For example, the red goes so to the union of the three, the blue goes up there, the green up there, and so on. And so as I told you before, we had a double aim. The first thing was to find something like this, so an abstract tree substitution like this. And the other one was to take this tree substitution, embed it in the contracting space where the Rauzy fractal live, and get another tree there. Most of the times, when you embed this substitution inside the Rauzy fractal, you don't get a tree. For example, if you do 2 iterations only in the contracting space, if you see this really in a plane, you get some problem. You get some loop. And you don't want this. I mean, if you want an embedded tree substitution, you want a tree also there. And so what you have to do, well, you have two possibilities. There are some trees which, for example, in this case, in the image of some trees, there are things that don't have gluing points, so there are only leaves here. They remain leaves for the entire process of substitution, right? So one possibility is to get rid of these leaves because they don't give you additional information for constructing the tree. So if you do this, we call this pruning process of the tree. So your abstract tree substitution, to get something that is really a tree also in the plane, you have to prune it. So this, for example, I will get rid of this leaf. But getting rid of this leaf, I have to define, I have a new element here of this kind, and I have to define where it's sent. Yes, you can prune also this leaf here. And so then you must define again the substitution on these new elements that you defined. So basically you end up with another tree substitution from the previous one, on more letters, on more subtrees, defined on more subtrees. And this basically gives you exactly a tree also in the plane, and gives you trees like this, like the one that I showed you at the very beginning. Okay? So the two-fold thing. You have an abstract tree substitution which converge to the repelling tree of the automorphism, and you have something that you can see in the plane where the Rauzy fractal lives, which gives you something like that. But you have up to pruning this tree substitution. Okay. So these were the first two theorems. Yeah, sure. You renormalize all the time. I mean, also the abstract tree substitution. You apply it, you get bigger patches, then you renormalize back. Yeah. And for the Rauzy fractal, the same. You apply, you get bigger patches, and you renormalize. So this is the first result about the abstract tree substitution that we get. So there's an algorithm which basically only consists in calculating singular leaves, singular words, identify them, and define an abstract tree substitution. And a second theorem that says, okay, this tree, you can prune it and see it in the contracting space of the substitution inside the Rauzy fractal.
Sorry?
Yes?
On the previous slide, you write in all our examples.
Yeah, very important remark. In all our examples, exactly. So I mean, we took examples and we could do this process. We didn't prove that for no matter which free-group automorphism, which is parageometric, substitution and so on, we can always find a tree by pruning. This we couldn't prove it. And so exactly this is what I write here. Embedded tree substitution, we conjecture that it is always possible to embed this tree inside the Rauzy fractal. the hypothesis that I said before, so free group automorphism that is parageometric, substitution which is also free group automorphism that is parageometric. Yeah, if you want to see it in the Rauzy fractal, of course, Piso, irreducible as well. Irreducible Piso.
So in this case, you always have a connected Rauzy fractal.
Yes, in this case, I always have connected Rauzy fractals, exactly. Yes, this is the parageometric case, yeah. And of course, I mean, when I give you an abstract tree substitution like this, there's no way, I mean, I chose this simplicial structure for him, for example. He could have just only put a bar like this with 2 gluing points. This does not depend on the simplicial structure that you put on the tree. The very important thing is that you don't have to touch the gluing points. And you can take maybe a spanning tree of these gluing points and so on. So what we proved also is that it does not depend on the simplicial structure that you put, because you will converge to the repelling tree of the automorphism. This is the other remark that I said. So then I have still 15 minutes, if I'm not mistaken, or 10 minutes, or 5 minutes.
2 minutes.
2 minutes! Oh my God. So the goal. The goal was... I thought that I had 10 minutes.
Well, 20 past, you should have.
Okay, yes. So, why we do this business? Why do we do this business? Not just only because we don't know what to do, but because there's maybe some dynamical importance. I mean, when we start with this subshift, having a tree and doing the contour of this tree will give you something like a circle, right? If you have a contour, a way to make a contour of this tree will give you something like a circle. And then you have a domain exchange, for example, or some isometry, some translations on these trees, right? This gives you some more dynamics also. So this will give you maybe something. And so what we wanted to find is something like an interval exchange transformation which factors down to this original subshift that we considered at the beginning. This was the main motivation. Why? So this is supported by things like Arnould-Cos interval exchange transformation or Rauzy words, so that are special words constructed with free substitutions by using free substitutions, which we know that are also codings of 6 interval exchange transformations. And this is also a very nice paper by Xavier Bresson and Yann Julien, where they considered this problem in 2012. Okay. So this was the motivation. So why, with our construction, we can do this? Because, I mean, when we have an abstract tree substitution like this, it's easy to find a contour substitution. Or maybe this deserves the blackboard again. So I just take, again, my trees, labeled by 3, 2, and 1, and this goes to this one, right? 1, 2, and 3. So once I've fixed some kind of order at the branching points, because I want to do a contour, right? So for example, if I'm starting here from this tree, I want to do the contour. So I just start, and then here I have a branching point, so I have to fix an order to do the contour, and then I can complete the contour, right? When I fix this order here, and for example also here, then I can say that the arc A12, because I'm in the subtree A, so I label the arcs with the gluing points A12, A23, and A31. This arc is sent by the tree substitution to the arc that connects 1 and 2 also in the image, right? So to this union of arcs. And this in particular is A23, this is C11, and this is B21. So in this way, very easily I get a contour substitution key here, fixing these cyclic orders at the branching point, right? So in this way, I have something that describes my contour of the tree. This is over 6 letters, and for example, it's characteristic polynomial Tribonacci times anti-Tribonacci in this way. So this is about the cyclic orders that I was saying. So you have to fix them in a somehow compatible way. And then you have a parameterization with the circle. So you do the contour of the tree. And this contour basically is a circle divided by 6 intervals, 1, 2, 3, 4, 5, 6 intervals, each labeled by one of these letters of my contour key. And so I have a way to give again addresses for each point of the contour. The addresses are given again by some substitution paths right now given by key. Okay, so this is some standard construction where that says, okay, I have a point of the contour and I can localize this and give an address that is called gamma, that is a kind of path A0 that goes to A1, that goes to A2, and so on. So I apply the substitution and I refine the intervals to see exactly where the point is. Okay? I'm sorry, but I have to go a little bit faster right now. And then what you have, well, if you have some kind of path like this, and you have also a notion of dual substitution for the contour, that I showed you at the first slide here, we can define a precise dual substitution also for this contour. Then you can inverse the paths. And what you can do is basically applying a Vershik map on this kind of paths here. And this Vershik map on these paths described by the dual substitution will give you exactly the piecewise rotation on the circle on these intervals. So this is a little bit fast, I must admit, but I can explain to you, of course. So the Vershik map on these kind of paths that are addresses by this dual substitution is pushed forward to a rotation on the unit circle, piecewise rotation on the unit circle.
Piecewise rotation is interval exchange, right? Or is something else?
Yeah, piecewise, an interval exchange on the circle. Yeah, on the circle. And so then you have to take care only about where the Vershik map is not defined, because I mean there's a set of maximal paths where that are exactly the empty suffix paths where this is not defined. So you have maybe to add some singularities because of this, and then you get really your piecewise rotation on the circle. In that case of Fibonacci, we get exactly the Ranuyokos interval exchange transformation. So I mean, this is what we get. I mean, I don't know if you can see it, but for example, here you have the red and the pink one. This is the first partition of the circle, and this is after piecewise rotation, no? The biggest one. It's just a fancy way to represent it. So you see that the red and the pink one, in the image, they are swapped. And the same for C12 and C21 that are here. And the green and the green here are also swapped. So this is basically also really the Ranuyokos interval exchange on 6 intervals. And so we get such kind of things for any parageometric free group automorphism, substitution that is a free group automorphism also. And so this is the things that I told you right now. And there are many questions, of course, many things that we didn't do yet. So we can, of course, try to generalize things with aesthetic. In the aesthetic frameworks, it means where the induction is just not just only the same substitution, but you change rule of substitution. The non-parageometric case seems a little bit more difficult. The embedding of the tree in the contracting space, I think that we can master it, but it's still work in progress. And of course, we would like to know what happens. We have a huge class of this kind of interval exchange under circle. We would like to understand more their dynamical properties, of course, that we get. We would like to know if they're weakly mixing, for example. What is the covering degree of the interval exchange and the substitutive system in this way? If they are very spatial structures, so to say. Okay? Thank you very much.
So this automorphism of the free group with which you started, how does it act on Kähler-Voigtmann outer space?
How does it act? I don't know this. Maybe Arnold can say something about this, but I don't know.
North of dynamics, there are 2 points.
So which one? So you have this tree one.
The tree is the weighted one.
And the other one?
And the other one is Naprienko.
Which one?
Which one is the one he is considering in the weighted one?
Yes, but which is that right? What is
The attracting is the one that is associated to the sigma minus 1.
The weighted one for the inverse.
And in this case, it is an intervolution.
And in this case, it is no, an interval translation of no.
For the inverse. This is come from a Silvanus also.
Okay, maybe we should postpone this conversation to lunch. Is there any other very quick question? Okay. Thank you again.
Start our afternoon session, and it's my pleasure to introduce Yaroslav Naprienko from Moscow, who will speak about convergent asymptotic expansions for Gaussian ensembles.
Does it work? Does it work? Yes? Okay, that's great. Then I want to thank the organizers for this conference. I'm happy to be in Pisa. So yes, I'm going to tell you about convergent asymptotic expansions for Gaussian ensembles. First of all, I want to define all things I'm going to work with. And the main definition is Wiener matrix, and that is the key object I'm going to work with. That's just a random matrix. That means that it's in 3 random variables. It's self-adjoint, and there are 2 conditions on this matrix. Above the main diagonal, all the random variables are IID. They have 0 mean. Oh, I can point, yes. 0 mean, they have variance equals to 1, and on the main diagonal, all the random variables have 0 mean, they are IID and finite variance. So, this class of random matrices is very important because for them, Wiener theorem holds. And this theorem states that the scaled empirical spectral distribution of eigenvalues, that's just a sum of delta measures. Slowly? Okay. That's just a sum of delta measures sitting at eigenvalues of my matrix. It is scaled by the square root of n, and we take the average sum, and it converges weakly to the Wigner semicircle distribution. Why it is semicircle? Because because of this. Okay. So, equivalently we can say that if we take a bounded function and if we take an average against this empirical spectral distribution, that's our test function, bounded function, we have this convergence. Kostya taught me that I can use colors in my presentation to show me, to emphasize something that's important, and in my presentation by red color everything that I'm interested in. Red color is what I'm interested in, everywhere. So, now we can see that we have this convergence by Wiener semicircle law. That is our main term, and there is some corrections. And I'm interested in these corrections. So, again, we have special matrices. For them, a certain theorem holds. The main leading term is Wiener semicircle distribution, and there are some corrections. Here, beautiful pictures. That's just a simulation on Wolfram Matematica package. I just took some random variables, just put it in the matrix, and indeed it holds. I checked it, it works. Okay, again, this formula is exactly from the first slide, just for your convenience. And it can be proved that this correction has the following term. It has no logarithms in denominators or any different things. It's just a series of negative powers of n. So again, red color, I am interested in these coefficients. So we have this quantity, that is our leading term, and smaller order terms I'm interested in. This expansion does not converge in general, so that is not a real series, a real sum. That is an asymptotic expansion. That means that if we take some m and truncate this sum, then the tail goes to 0 faster than this finite sum. So that's asymptotic expansion. And I'm interested in this red thing. Okay. Again, I'm going to reformulate it one more time. If we consider the eigenvalue density, if somebody likes the language of point processes, that's just the first correlation function, we can then define the eigenvalue density function Pn. That is just if we integrate a bounded function against this density, we have exactly what we are looking for, average of a bounded function against empirical spectral distribution. So that's just very convenient for me to work with this object rather than this, because it's easier to write. It's very difficult to write, and it's easier to work with forgetting about random matrices at all. Because now, as we can see, that's just the same what was on the previous slide. That's all absolutely the same. Third time, that's absolutely the same. And this formula is so important, so it is here. That is the only numbered formula in my talk. And 1 is always means this. 2, there is no 2. Only 1. Okay. And I'm interested in this. Here it's red 2. In this alpha key. This alpha keys. So, that's my question. I'm going to discuss. But I'm interested in special cases of Wiener matrices. Not all matrices, but only that are very important in the theory of random matrices. The first ensemble, that's just a set. Ensemble, Gaussian unitary ensemble. It's a set of Wiener matrices such that we know the distribution of its entries. In general, Wiener matrices, we don't know that. So, on above the main diagonal, the random variables are normally distributed with 0 mean and variance equals to 1. And note that it is complex random variable, so it means that real and imaginary parts are normally distributed. And on the main diagonal, we have identically distributed independent random variables with 0 mean, normally distributed with 0 mean and variance equals to 2.
They are real.
Yes, they are real, of course. And Gaussian orthogonal ensemble is absolutely the same, word by word, except that, above the main diagonal we have also real random variables. That's the only difference. Everything else is the same. So I defined very important classes for me, and there are particular cases of much more general beta ensembles corresponding to beta equals 2 and beta equals 1. That's just something we are going to discuss later. So, what we have up to now? We have some classes of Wiener matrices. They are Wiener, so for them, Wiener semicircle law holds. So we have this distribution, and for them we can ask this question: what are next correction terms? So now my favorite slide. That's the table of results. What results are done for different random ensembles? So coefficients, still TS, Laplace, ODE, and convergence are different classes of results that was done for different random matrices. Coefficients in the expansion 1. These coefficients for Gaussian unitary ensemble they were found in 2012 by Hagerop and Torbenson. Still TS and Laplace stands for still TS transform and Laplace transform. I'll discuss it later, but they're important results on random matrices. ODE is an ordinary differential equation for the density. We discussed what is density. For the density for Gaussian unitary ensemble and for Gaussian orthogonal ensemble. And convergence is when this asymptotic expansion is indeed convergence. So it's just a real sum. So we can sum up and to get the result. Note that for Gaussian orthogonal ensemble, no, 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 and no. And they are red. that means that I'm interested in this nose. And the purpose of my work is to remove this no and to place yes there. So that is, that is my goal. So let me discuss some history of this topic. In 1986, Harer and Zagir found the expansion for moments of Gaussian unitary ensemble, and they were not interested in random matrices at all. They counted maps of certain polynomials with fixed number of edges and vertices oriented and one seller on the plane, and so by accident it was exactly moments of Gaussian unitary ensemble, so they found explicit formula, asymptotic expansion, and they found coefficients. So, okay, we have asymptotic expansion from 1986 year. So, in 2003, Erkovani and McLaughlin proved that this expansion in this form, so we indeed have negative powers of n, exists for Gaussian unitary ensemble. So we really may ask this question about these coefficients because it really exists. In 2003, Hogerop and Jorgensen found Laplace transform for Gaussian unitary ensemble. You see? Yes, here. In 2005, Gertz and Tikhomirov found differential equation for density of Gaussian unitary ensemble, and we have yes here. In 2012, Hogerop and Jorgensen again found coefficients, and that's my main interest, coefficients and Stieltjes transform for Gaussian unitary ensemble. So, and we see that coefficients yes, Stieltjes yes. Wonderful. In 2013, Borot and Guillenet proved that expansion exists for general beta ensembles. That means it exists for Gaussian unitary, for Gaussian orthogonal ensembles, for many different ensembles, including my main object of interest. In 2014, Witte and Forrester found first 6 coefficients for general beta ensembles. That is not indeed expansion, but only a part of it. They don't know next terms. And it works for Gaussian orthogonal ensemble as well, partially, because it's a particular case of beta ensembles. So you see there is a star. They did not find all the coefficients, but something they found. And in 2016, Kapilevich proved that this expansion is really convergent. So it's a real sum for a certain class, I will describe it later, for a certain class of entire functions if we consider a Gaussian unitary case. So that's history of results, and I'm going to answer on these questions in my talk. My main result. If we take density of a Gaussian orthogonal ensemble, then there exists an asymptotic expansion. So basically I can prove that existence, forgetting about these results. And I know explicitly the coefficients in this expansion. They are not very beautiful, but they are explicit and we can find them. And they have the following formula. That's a finite sum. There are some constants that can be calculated recurrently. I will explain, it's very natural why they're not explicit. That's just in terms of Chebyshev polynomials with a certain weight and f derivatives of f. So basically, if we take a bounded function, smooth bounded function, we can write this asymptotic, not convergent yet, asymptotic expansion, and we know coefficients explicitly. So we found coefficients. That's great. That means that one, yes, we have. Next, if f is an entire function of order of growth less than 2, then this expansion from the previous theorem is convergent. So that is not bounded function, and that's why it's not trivial, because all these results are for test functions. Test functions are usually bounded. But here we can take an entire function, and for an entire function this expansion is convergent too. Okay, what we have up to now? We have table, we have my object of interest, Gaussian orthogonal ensemble. I'm going to answer on these questions, and just now, and right now I stated 2 theorems I proved, and now before I'm going to give an idea how to prove these results, Not too fast. Yeah, boring. Okay. I want to tell about the main instrument that was done for Gaussian unitary ensemble case. Gaussian unitary ensemble is the most studied case in the theory of random matrices because of the symmetries, because of a lot of simple formulas. So, and here again, I told you already about differential equations on the density. Here y for the density, and our density satisfies this differential equation. What is important here? It is very important here for this problem is that only one term has a factor depending on n. Only one term, and that is crucial for their work, for their job, for their method. Only one term has this factor, all other factors does not have anything depending on n, and it helped them to get their results. But in 2014, Witte and Forrester found differential equations for the Gaussian orthogonal ensemble, and we see that a lot of terms have coefficients depending on n, and their approach does not work here at all. It's impossible to follow their strategy. It's necessary to figure out something new. I want to emphasize that this differential equation, and probably not this, but this differential equation was the main instrument for Hogerop and Torbenson for proving all the results from the table. These results was proved by this differential equation, this by differential equation, differential equation, differential equation, differential equation. Everything was proved by differential equation. We can't use this huge formula and follow their strategy. And now I'm going to tell you the idea of the proof of what I have done. I will use key lemma. That is the most important instrument for me. Why? If we take density for Gaussian orthogonal ensemble, and if we take density for Gaussian unitary ensemble, then they satisfy a certain differential equation. And why it is important for me? Because this differential equation is a bridge from Gaussian orthogonal case to the Gaussian unitary case. See, there Gaussian orthogonal ensemble density, and here we have Gaussian unitary ensemble. So in some sense, using this differential equation, we can reduce questions from Gaussian orthogonal case to the Gaussian unitary case. Of course, with some payment for that, but that's it. So that is my strategy in 4 steps. The first step, I'm going to use this differential equation, and I'm going to calculate Stieltjes transform of these densities, and to find differential equation that links Stieltjes transforms of Gaussian orthogonal ensemble and Gaussian unitary ensembles. So now I have this bridge between Stieltjes transforms. It was between densities, so we can go to Stieltjes transforms. Second, we can expand in this expansion. Imagine that here, I will explain what is Stieltjes transform in a minute, don't worry. So we can expand Stieltjes transform in this asymptotic expansion, and we can equate coefficients from both sides, and to get system of equations from which we are going to derive coefficients of expansion. If you lost, don't worry, because on the next slide I will be discussing all these things in details. That's just outline. So I'm going to equate coefficients to find a system, a recurrent system, and to solve it. That's a system of differential equations. Using
When you differentiate this P for n, it's in a mixed sense, right? In the sense of distributions.
what do you mean?
The density is the sum of delta functions, right?
No. Yes.
That's correlation function.
Yeah. For Gaussian unitary and for Gaussian orthogonal case, they are explicitly calculated. Okay, special for you. I have almost at the end explicit formulas. Well, that's it. Explicit formulas for Gaussian unitary ensemble case and for Gaussian orthogonal case, but they're quite complicated, and I'm not really interested in their formulas, so I'm not going to discuss them. But they're continuous. That is not distribution. That's just continuous smooth functions.
How often differentiable are they?
As many as you want. Yeah, infinitely. They're very good. Okay. So, yeah, so what we have? We have this key lemma that is a bridge between two ensembles. And now I'm at the point that I have a bridge between STU-TS transforms. Now I'm going to reverse STU-TS transform and to find the coefficients for this expansion. I will discuss everything in details, don't worry. And then I will show that this expansion is indeed convergent. So here 4 steps. I link these two ensembles to get all results I want to get. Let's go to the first step. The first step we have, that is exactly our bridge, that is key lemma, differential equation. Very easy. Multiply by f, integrate by parts. And we have something like that. We have equality. This thing is integrated against density of Gaussian orthogonal ensemble, and here a Gaussian unitary ensemble. Now let me recall what is STU-TS transform. It's time to recall what is that. It is defined by this integral. We take a special function s minus x to the minus 1 to minus 1, and we integrate against a density, and we have a function on parameter s, and this function is very important in the studying of random matrices because it's connected to resolvent and it shows a lot of properties of random matrices. Usually it's more useful for us Fourier transform, but in the theory of random matrices, STU-TS transform is much more important, in my opinion. So we have this, that is the definition of STU-TS transform. And again, it's important, and again, it's the function of parameter s. But here we have this equality for arbitrary function f. So let's take this f equals to s minus x to minus 1. And so we have, on the next slide, again, for your convenience, that's the same equation. If we take a certain function, STU-TS transform, we can easily, after some extra work, like integrating by parts, we can easily get this differential equation that's, again, a bridge between STU-TS transform of Gaussian orthogonal ensemble and STU-TS transform of Gaussian unitary ensemble. So now we have a bridge between STU-TS transforms. Now let us write an expansion of this density of these STU-TS transforms. We have expansions. Here it's red, so I'm interested in these values. I write these expansions and I want to put them here, right into this differential equation. If I do that, there are some technical details. I need to prove that these functions are indeed analytical on S, so I can differentiate it term by term. There is some technical routine, but after that, when I put them there, right into this differential equation, I can equate coefficients in this asymptotic expansion, because every time I can tend n to infinity, and I have only terms that survive, and they gives me some differential equations, a system of differential equations. The first one is special, the second one is special because we have here n squared, n, so at first steps we won't have a general formula, and then we have a general formula. And from the results of Hogerop and Jorgensen, we have coefficients for STU-TS transform for Gaussian unitary ensemble. And that's what helps us after all. Now we have right sides recurrently. See, the first here we know. So that's just a differential equation, we can solve it. Here again we know from the previous step the all right side, so we can again solve this equation, and we can do it repeatedly, and we have these coefficients that can be calculated recurrently. There is some formula, I'm not going to write it down. So after all, we have explicitly coefficients of asymptotic expansion of STU-TS transform of my measure Gaussian orthogonal ensemble density. That's what we have. Let me recall again what we are going to do. We're using this key lemma. We are going to try to write down differential equation that links STU-TS transforms. When we are going to equate coefficients to get coefficients of STU-TS transform for Gaussian orthogonal case. And now I'm going to inverse my Stochastic transform to get coefficients for general case, not only for special case when f is s minus x to minus 1. I'm not interested in the special case, I'm interested in the expansion at all, in general. So now I have these coefficients, and now my purpose is to inverse this formula. That is not very easy, but it is not very difficult. We can, by expectation, by looking at this term, we can deduce that actually this term corresponds to the Stochastic transform of this function. So it is somehow a trick. So I want to find these coefficients by natural and obvious observation. If we have equal Stochastic transforms, we have equal measures from the very beginning. So because everything is smooth and everything is all right. So that's why I can inverse this Stochastic transform, and using, you see, that's quite, you see, that's a trick. That's not very natural maybe way, but that's indeed a way how we can get these coefficients explicitly. So if we deduce from what function we have this Stochastic transform, we won, okay. And these functions are okay. They work for us. So, again, for the same constants that can be calculated recurrently, we found these coefficients. So, finally, I can make a tick here. Coefficients are found. There were 4 questions. Oh yes, 2 TS are found too. Great. So we have 2 yes in my table of results. Now we have coefficients, and now we have still TS. We know expansion of still TS for Gaussian orthogonal ensemble. We deduced that from the Gaussian unitary ensemble by reducing using this key lemma. Key lemma is a bridge that helps us to connect these 2 ensembles. It helps me. So what we have? We need to show the convergence. How much time do I have?
Well, you still have
20
20 minutes.
minutes.
23.
23? Oh, I'm too fast. All right, you see.
Don't worry about it.
Okay. Okay, so yes, it's better to be slowly. So let's go. So now we have these coefficients. Yes, this I showed you already. So it remains to show convergence of the asymptotic expansion. And now I want to show the theorem of Kapelevich. Kapelevich in 2016 proved the following theorem. This theorem is quite a technical result maybe, but it's not trivial at all because test functions are usually bounded functions. But he showed that this expansion for Gaussian unitary ensemble, not orthogonal, unitary. Everything is known for unitary. And he showed that for unitary ensemble, if you take an entire function of order less than 2, or maybe equal to 2, but then you need to have a finite type. And let the density be, let P be, okay, that's just our eigenvalue density function for Gaussian unitary ensemble. Then for large enough n, that is not statement for all n's, but if we take large enough n, we have convergent expansion. So this series is really a sum. So we can, and these coefficients are known, are explicitly calculated. They are from Gaussian unitary ensemble. They are not like calculated by me. So, but this expansion holds and is convergent.
So alpha J is.
Yes, you're right. No, not key, yes, J. Okay, yes, indeed. Thank you very much. And now, what we have? Now we have a bridge between Gaussian orthogonal ensemble and Gaussian unitary ensemble. And we have a result for Gaussian unitary ensemble. So it's tempting to try to just reduce a question for Gaussian orthogonal ensemble to the Gaussian unitary ensemble using Kapelevich theorem. And it works. That is a little bit technical result, but it works. And what we are going to do? One of our steps was this formula. And when we multiplied my differential equation by f integrated by parts, we had this formula. Now, if we consider this left side, we might write a differential equation like that when we take a function g to be our entire function we're interested in. There is a result that is quite new. It was about 2 years ago by Hetoganga, Korhonen, Eratia. I don't know exactly how to read them. That solutions of this differential equation for an entire function g has the same order of growth and the same type. That means if I start with a function g, for example, of order less than 2, then this solution is also an entire function of order less than 2. So basically we can replace it here. So we have our integral of g against this density we're interested in. It equals to this expression. This expression equals to this expression. And in this expression we have prime f. And we know that derivatives does not change order of an entire function. We can differentiate it and order will be the same. And multiplying by x does not change the order of an entire function. So after all, we have that this expression we have equals to this one. And here we have exactly a function, an entire function from the class we're interested in, from the class of Kaplevich's theorem. It would be an entire function of order less than 2 of finite type. So we might just reduce the question of orthogonal case to the unitary case by using these properties of solutions of certain differential equations. That's crucial here that we have only x squared here, because the solution has the order of, for example, if it would be x to the 3, then the solution could be grow too fast, and it would not be the case. But here everything is great, and using these results, using the properties of solutions of differential equations, we have everything we need. We started from an entire function g of order less than 2, solve this differential equation, put it here, it equals to the right side. That is again an entire function of the same order we are interested in, and this expansion is convergent by Ofer-Kaplevich's theorem. So basically, yeah?
The function f that solves this differential equation will depend on n, right?
Huh?
The function f which solves the differential equation is a function fn. It depends on n, right?
Yes.
So you apply Kaplevich's theorem to a sequence of functions?
Let me see. Okay, maybe I need to make some extra work to show that this sequence of functions is also convergent where I need. No, I can't answer right now. Okay, yes. Yes, this differential equation depends on n, so probably it's better to try to use something else. Okay. Okay. I'll think about it. Thank you very much. So, if it works, then we reduce orthogonal case to the unitary case, and we have convergence. So it is not very. It would be like that. I'm not sure. Now I'm not sure. Maybe. Okay. Maybe we have this result too. Next. We have let us return to this table. So we have coefficients, we have still TS. Let's skip it. Oh no, let's keep it convergence. And now we have Laplace. So Laplace transform was found by Hagerup and Turbinson in 2003, and it was an interesting work because they found Laplace transform and they reproved all the results about random matrices, like distribution of largest value, distribution convergence to y-asymptotic law, everything they could reprove just using Laplace transform. So it was interesting to find, they explicitly asked in their work if it is possible to find explicitly Laplace transform for Gaussian orthogonal case. So I decided to find it, and here it is. Laplace transform. Laplace transform is defined as integral over density e to sx. So this term goes from Gaussian unitary ensemble case. So this term was known. This term was unknown. This term was unknown. I found them, but Pn I found the. Okay, this Pn is a certain polynomial. This polynomial, we know all the properties of this polynomial. For example, degree, coefficients in some way, it's the differential equation it satisfies. But I can't write it like some known function, a special function. Like that is not Hermite polynomial. That is not hypergeometric function. I tried to find, but nothing works. I found it as the sum of hypergeometric functions with different arguments. That is not a very good solution. So I decided to put it like that. So that's a known polynomial, and we know all these properties. And so we can find the Laplace transform. And using this Laplace transform, we can actually reprove all the results about random matrices. For example, convergence to y semicircle law, distribution of largest eigenvalue. It is almost sure less than 2. Yes. And I think we're going to the end. That's just a slide for somebody who are going to ask me what is densities of Gaussian unitary and Gaussian orthogonal case. That is the reason why differential equations are difficult, because that's indeed just Christoffel-Darboux kernel, and we know all the properties we can differentiate and get a very simple formula. So we have a very simple differential equation for that. But Gaussian orthogonal ensemble is rather complicated. It has some terms. Purple is not necessary to read, like in Costa's presentation. So that is rather complicated, and if you want to write a differential equation, it would have 5 order and a lot of terms. So that is not appropriate for strategy of Gerop and Turbinson. And now I want to speculate just a little bit. See, in our table, we have another no I'm interested in. See, here we have yes for ordinary differential equation. For Gaussian orthogonal case, also yes. But for beta ensembles, that is no. And that's what I was going to do next. I'm interested in finding ordinary differential equation for general beta ensembles because I can repeat my strategy. I could try to reduce it to lower betas. I can find two differential equations, to test transforms, and to find convergent asymptotic expansion. So the main instrument for me is ordinary differential equation for the density, but it is unknown by now. But what is known? It is known for Gaussian unitary case. For Gaussian symplectic case, I didn't discuss, but it is quite similar to orthogonal case. That's just another case of Gaussian ensembles. It has order 5. It has order 3. Orthogonal case has also order 3. So we conjectured that for uneven beta, we can write a differential equation of order beta plus 1. Despite Forrester in 2006 found explicit formulas for eigenvalue density for even betas, they are really complicated. They are huge formulas that is absolutely impossible to analyze to find differential equation, for example, of this order. So I tried, and it was not so easy. I couldn't do that, and so I think maybe it's possible to consider this question going back to the definition of beta ensembles. So we can write explicitly this common distribution of eigenvalues, and we know that the first correlation function is just many integrals n-1 integrals of this common eigenvalue distribution, and so this is indeed the probability density, the eigenvalue density. And so I study this object now, and I found some evidence that it is indeed of order beta plus 1. And I think from this method it's possible to prove, and I think maybe it is possible, and I'm going to tell you next time. So, and thank you for attention.
So the convergence to the Wigner semicircle law also holds almost surely.
Yes, yes, of course.
And I guess there's probably a known optimal error bound. I don't know for that.
You mean for general bit for general?
No. Let's say for your favorite GOE. But you could also, instead of taking expectation value with respect to the natural Gaussian measure, you could change it slightly. Are there? I mean, there are of course recent results by Yao and so on convergence to semicircle law for very singular measures. But are there any other cases known where you have a complete asymptotic expansion for other than Gaussian measures?
Yes, it is known for not only Gaussian beta ensembles that includes Gaussian orthogonal and Gaussian unitary. It also holds for Gaussian circle, or for circle beta ensembles. That's also a generalization of circle ensembles, and it also known for some class of invariant ensembles, but I don't remember the definition.
But for circular ensembles, it's just uniform distribution on the circle.
Yes.
So there's no expansion, no? It's just the identity.
No, we can consider, like in this Gaussian case, general beta. So
okay, for general beta.
Yeah, for general beta.
And then you get a complete expansion.
Yes. It is probably this, not in the same work of Forrester and Witte, but in the next work, maybe in the same year, 2014.
Okay.
They have several results, several papers, and first Gaussian, then circle, and they discussed it.
Great. But for changing the Gaussian in your case?
No, I didn't do it yet.
Thank you.
Do we have any further questions?
So getting back to this operator between functions of order 2, isn't it a bounded operator? So if you have convergent sequence Fn on one side, then you have convergent sequence Gn on the other side, and you can apply just without any extra difficulty.
I mean this?
Yes.
I hope so. I don't know now.
I hope so too.
It's necessary to prove, but okay.
Okay, any further questions? Then let's thank the speaker again. And we meet in 40 minutes to listen to Corinna.